Okay, fine. Just before I start, a final issue that I want to mention to you. If you look at the documents that are available on my website, I'm now jumping to this one, the case of the Emilia-Romagna region. And I didn't show to you these two documents. The first one is a paper, and it's a scientific paper which is emphasizing the relevant role that in hydrology and water resources management is played nowadays by change. Climate change, environmental change in general. It's a scientific paper. It's not needed for you as a background for your exam. I think it's just an interesting paper that you may want to read to better understand what are the key challenges today. I mean research challenges for hydrology and water resources management. This is a supporting information. I think it's useful for you to read some scientific papers besides tutorial documents, and therefore, you know, I think it was an interesting reading. But I am biased because I am one of the authors of that paper. So, in any case, the important thing is that you don't need to read it. In the same way, the other document, History of Water Supply, it's just an excerpt, some pages are extracted from a book which describes some details of the history of water supply. Again, I'm not at the exam, I'm not asking any question on the history of water supply. I just thought it was interesting. If you are interested and passionate about the history, it's an interesting reading. And now let me move to this case study, and let me explain to you what is the reason why I am presenting this case study to you. First of all, let me switch off the wireless, otherwise we are getting bored by these messages. And again, I think that it's a useful introduction to the problems, typical problems of water resources management, if I present to you a case study which refers to the region where we are here now. And the case study, I think it's useful because water resources management is a practical problem. It's a practical problem whose solution very much depends on the considered case study. In water resources management, the governing principles are very general, and the governing principle doesn't lead you directly and straightly to the solution. It's important that the governing principle is applied to the considered case study, and the methods for the application of the governing principle are very diverse depending on the case study. So when we talk about methods in water resources management, you have a diversity of methods available, and therefore the selection of the best method depends on the case study, which means that in this particular scientific field, the case study plays a relevant role, because, as I said, the governing principle is very broad, and in order to identify a method for the application of the governing principle, let me provide to you an example. The continuity equation, mass balance equation of water, this is the basic governing principle of water resources management, which leads you to the solution of your problem. But in order to identify the method, I forgot to switch off this one, sorry. In order to identify which method may lead you to the application of the governing principle, you need to consider your case study. So basically, case studies are providing to you the necessary information, and therefore we have to get used to understand what are the challenges and what are the behaviors, the features of the considered case study. So if you have a client that comes to you and says, we don't have enough water in our town, you soon have to realize that the first thing that you need is information on the case study. So which kind of water supply do they use? What kind of water supply systems is in place? How much water is available for the considered case study? And therefore you directly jump to the case study. Let me introduce in formal terms the governing principle that I mentioned to you, which is, as I said, the mass balance equation for water, which is also called the continuity equation. This is the governing principle, the one of water resources management. It's the basic one. So basically, in order to apply this governing principle, which is again the mass balance for water, you know, it's very useful because mass balance means comparison between water availability and water demands. In order to apply this governing principle, you first of all have to identify the domain to which the mass balance of water should be applied. The domain could be, for instance, a city, could be a water supply system like an aqueduct, could be a part of territory, of land, like the catchment, which I will define soon. And once this domain is identified, the mass balance equation is written in this way. If you identify the volume of water which is included in your considered domain with W, which is a time-dependent variable. Again, what is WT? Is the volume of water which is included in your considered domain. Again, the domain could be an aqueduct, for instance. Okay? The mass balance equation says that the change in time in differential form of this volume of water is equal to the inflow into the domain, which I will call with the symbol QT, which basically is water flow into the domain, water flow into the domain minus the water outflow, which I will indicate with the symbol DT, which is water withdrawal. Water withdrawal, let me add flow. These are flows. Flows, I already provided a definition of water flow. It's volume per unit time. So basically you see that on the left-hand side, you have the change in time of volume, so volume divided by time. In the right-hand side, you have flows, which are volume per unit time. So in terms of dimensions, this is coherent. And in the right-hand side, you have water flowing into the domain, which is basically water availability, and then minus water demands. This is very simply the mass balance equation or continuity equation, which you need to apply basically in very understandable words. You have to compare demands and water availability. It's very simple. And if you have more demands than availability, you can still survive if you have some volume of water stored in your domain as a reserve. Think about, for instance, an aqueduct. If you have a reservoir storing water, then you can still keep the system going and functioning even if you have more demands than water availability. But of course, in the long term, you have to get a balance among availability and demands, or more availability than demands. It's very simple. And basically what I want to anticipate to you, the technical, let me say, the theoretical solution The governing principles to water resources management problem are very simple. You see, it's a comparison between availability and demands. What's difficult is the application, because you may have not data to estimate water demands and water availability, for instance. And therefore, you have to invent solutions that allow you to work even if you don't have any data. And these solutions depend on the case study. For instance, data availability matters a lot. So if you have a case study where you have a lot of water available, it's one story. If you don't, a lot of data available, it's one story. If you don't have any data, it's another story, and the methods for solving the problem change. So I think it's important that we try to understand what is a typical case study. And this is a quite simple case study, but still the solution is not so straightforward. I say that this case study is simple because, you know, the problem here, as you will see, is not a problem of water for civil use. It's a problem of water for food, which is not very relevant because the problem, if one looks at the detail, is to make sure that there is enough water to produce the Parmesan cheese, which is very important from an economical and societal point of view, because the economy of this region, as you may know, is also based on the production of the Parmesan cheese. So if people and farmers are no more able to produce the Parmesan, the consequences are economically and societally relevant. But still, you can understand that this is not a problem of make sure that life is possible. I mean, it's not a problem of people living or dying. It's a problem of making sure that people can get some money from their work. It's let's call it a minor problem. Yeah, sorry for that. Okay, so let me describe the problem very quickly, because it's important that you get an idea, but I don't want to go into the details now. Also because to go into the details, you need some background, which I will provide to you later. So this is the region I'm talking about. You can see, I'm sorry, maybe I can try to lower. I'm not sure if I have the opportunity of switching off some of the lights only. Let me see. No. Okay. Could be. No, this is too much, but I'm thinking it's a bit better. I hope so. So you can see a map of Italy and the location of the region. And this region is, it's characterized in terms of river network. There is the Po River that draws the north boundary of the region. So in the upper part of the region is extended up to the Po River. And the Po River flows from west to east here. So it comes from the Alps, so up here, up there, and then flows in the upper part of the region. So it's this one. And then you have several rivers that flow in the south to north direction, which brings the water down from the Apennines to the Po River. And these rivers, the Po River and the Apennine rivers, were traditionally used in the past for water exploitation. And in particular, the Apennine rivers, they provide very good water. The quality of the water is very, very good. The quality of the water of the Po River is not that good, as you may know. It's improving, but it's not that good. Keep in mind that probably I already mentioned to you this, that up to 1930, people used to drink directly the water from the Po River. And then pollution increased, and typically in Europe, river pollution increased up to 1980-1990, and then some European policies were developed in order to make sure that river restoration could take place. So basically now the water quality, the surface water quality in Europe and also in Italy is improving, but still the quality of the Po River is not really very good. You can't use it directly for drinking. You can use it for irrigation, but not for drinking. And instead, on the other hand, the quality of the water from the Apennine rivers is still very fine, at least in their upper part, of course. So it's a region that also is characterized by the presence of an extended aquifer. In the flat part, the green part, there is an extended aquifer, which is basically unconfined, and which is very rich of water. And therefore, traditionally, people take the water from the rivers, and then, especially during summer, when the rivers get dry, they get water from groundwater. When you get water from groundwater, it's a bit more expensive because people need to pump it, and therefore there is an energy consumption which translates in money expenditure. Okay, let me move forward, and again, the practical need here is, I'm not sure, let me just read here, but I anticipate that the practical need was already introduced to you, is to make sure that there is enough water for producing the Parmesan cheese. And basically in this region we have enough water for seaweed use, and we have some problems with the agricultural uses, and in particular for the production of the Parmesan cheese. What I mean with production of the Parmesan cheese is water for irrigation, to irrigate the fields where the grass is cultivated to feed the cows to produce the milk. So the problem is irrigation of this grass fields. And traditionally, keep in mind that the Parmesan is an historical production, so this which started in the Middle Age, and at least in the Middle Age, maybe even before than that. And basically, so it's this cultivation of grass has a long history, and people used to irrigate these grass fields by using flood irrigation. Flood irrigation means that you take water, surface water or groundwater, and you let the water flowing over the fields. It's called flood irrigation. So you start from the upper part of the field and you release water, and the water flows down. Of course, while the water flows down, it infiltrates. So at the beginning of this process, you only irrigate the upper part of the field, but then the field gets saturated, and then water flows more downstream. At the end of the story, water reaches the lower part of the field, where there is a small channel which takes the excess water back to the surface network. This is called flood irrigation. And the advantage of flood irrigation is that it's inexpensive, or it's very less expensive with respect to other kind of irrigation. If you think of sprinkler irrigation means that you pump the water into some machines which throw the water by emulating rainfall over the field. This is called sprinkler irrigation. And we call it in Italian irrigazione a pioggia, which means rainfall irrigation, rainfall-like irrigation. And this kind of irrigation requires the use of energy to pump the water under pressure into the irrigating machines. So the reason why flood irrigation was preferred at the beginning was its relatively easy application. The problem with flood irrigation is that it requires a lot of water. It has been estimated that the amount of water that you need with the sprinkler irrigation is about 40% of the water that you need for flood irrigation. This is an unbelievable water saving, because 40% of the total means that you are saving more than half water, more than half of the water with respect to flood irrigation. The problem is that sprinkler irrigation, besides being expensive, it's also not really liked by the farmers, because they get convinced that it is not the optimal irrigation for the grass. Because, you know, sprinkler irrigation makes the grass wet during night, typically, because they are irrigated during night. And in the next day, if you have a lot of sun, they are concerned that, you know, the grass could burn. And we say it burns. Actually, it doesn't burn, but it gets damaged, because, you know, the sun over the water drops it's damaging the grass. And this is their concern, which of course doesn't happen with rainfall, natural rainfall, because usually when it rains you don't have sun. Okay, sometimes you may have, but it's very rare. So they don't want to use sprinkler irrigation also for this reason. And another feature of these fields is that they are never tilled. Tilled means arare in Italian, which means that once in a year you take the ground and you move it. You move it in order to start the next year with a new cultivation. And these grass fields are never tilled, which means that the grass is there starting, maybe in some cases it has been there for hundreds of years. And there is a convincement in the farmer of the fact that the grass is undisturbed is another peculiar feature of this region, which makes the Parmesan cheese unique. Because the reality is that we don't know why the Parmesan cheese is unique. If you try to produce the Parmesan cheese with the same techniques in a nearby region, you don't get the Parmesan cheese. So there is a different cheese which is called Grana Padano, which is lower quality. So we don't know, actually, we don't know why the Parmesan is unique. We don't know what makes it unique. So the result is that farmers and economical operators, they don't want to change anything because they are concerned that if you change irrigation from flood irrigation to sprinkler irrigation, the flavor of the Parmesan may change. Because actually, if you don't know why you get a unique product, of course you are concerned by everything. And they are also concerned that they start tilling the fields, they may lose this unique feature of the Parmesan cheese. So I think it's a very interesting problem, by the way, but still the problem now is that there is not enough water. This is a historical problem. Already about 200 years ago, people started to complain about lack of water in this region. And keep in mind that the Parmesan is not produced over all the region, it's produced in a very small area. So they started complaining already 200 years ago. And the problem is still there. And now it is even more concerning because we are required by the European Union to release environmental flow in the rivers. And therefore, the farmers cannot take all the water from the rivers like they were used to. In the past, they used during summer to take all the water from the rivers, and now they cannot anymore. And therefore, they are much more concerned now. So the problem became more concerning. So this is the practical need then. So the practical needs, the practical question is, how can I make sure that the grass fields for the production of the Parmesan get enough water for irrigation, even after the release of environmental flow? And how to solve this historical problem, which was never solved in the past, for many reasons that we will see. So this is our practical need. Some background, this region in the past it was a gulf of the Adriatic Sea, and then the siltation induced by the Po River filled this gulf, and therefore a very flat region was created. At the beginning it was a marsh, because the Po River was not drained, and when you have a so huge river that it's not drained, then you have frequent floods. Then people built the levees along the Po River to avoid flooding, and then they built the canals to make sure that in this flat area the rainfall is drained properly. And I mentioned to you that they created consortiums, reclamation consortium for managing the drainage of this flat area. We end in the summer irrigation. So basically now irrigation is managed by this consortium, and they get the water from the rivers, surface water, and from the groundwater when they don't have enough water into the rivers. And groundwater, usually it's not a problem, it's expensive, but there is plenty of groundwater in the area, but still some people are concerned because groundwater extractions are increasing. And of course, with groundwater, you never know what's going to happen in the future, if there is indeed enough water, if the withdrawal are sustainable, and etc. Okay, and here you have some historical background that I skipped, because I think we are not interested in the history of water controls and irrigation in this region. It's interesting, but I don't want to make this explanation of the case study too long. Here you have some pictures where you can see the rivers. This is a picture of an Apennine river. This is available on my website, so I don't spend much time. This is, it's not a natural lake. This is water withdrawal along an Apennine river, the same that we saw before. Basically, people started in the Middle Age, as I said, to take water from these rivers, and in order to take water, you have to build some facilities, like, for instance, canals. And in this case, they built a dam, a small dam. The height of the dam is less than 15 meters. And so this is not really a dam, because you may know that a dam is defined by a height of at least 15 meters and a storage of at least 1 million cubic meters upstream. In this case, you don't have so relevant storage. The height of the dam is less than 15 meters. It's not a dam. It's just a barrage, what we call a river barrage. And the barrage, in this case, is meant to store some water upstream, a reduced amount of water, in order to make the withdrawal possible and regular. Because if you have some storage, as I mentioned to you, even if you have demands that exceed the water flow, you may, of course, make sure that the system is still working because you use the storage. And here there are other pictures, and again, this is a barrage on another river, and you see the river here, and here the water that is diverted to the canals, to the irrigation canals. And there are some very nice, this is a fish ramp. I just wanted to show it to you, because today in Italy, but also I would say it's a policy, a European policy. We need to build a fish ramp every time that we interrupt the migration of the fishes along a river. So every time that we build a barrage, we need to build a fish ramp. This is another very interesting problem, because these fish ramp usually don't work. So the fishes don't like to go upstream along the fish ramps. And it's not well understood why this happens, because people usually try with several different solutions. The actual result is that one ramp over 100 on average works. And it's not clear why. There are, of course, the efficiency depends on the type of fishes, depends on the river flow that is released along the ramp. We are not dealing with fish ramps, but I wanted just to mention to you that this is indeed, in water resources management, is another relevant problem, at least in Italy. And it's one of the major concerns of a professional engineer that is called to design a water withdrawal, because to get the water from a river, you need to build a barrage, usually, unless you really have a huge water flow in the river. Usually, you don't have such abundance, you need a barrage, and then you need a fish ramp. And usually, you know, when you design it, then people come from the environmental agency, look at the project, at your design, usually they are not happy. And so this is always a matter of concern. I tell you, I gained some experiences in fish ramps, because usually professional engineers, they come to the university to ask for a consultancy, because this is a problem that is concerning for them. But actually, we have not really, in many cases, we don't have a good solution to suggest. And my experience so far has not been positive, because we did also some monitoring campaign to check what was the result, and the result is, in my experience, was always negative. Fishes don't climb the fish ramp. And there are other nice features. I wanted to put you here, this picture for you, because I think it's very interesting. And this is what is called, in Italian we call it a partitore. I would say that in English we could call it a partitioner, which means that in the Middle Age, because this kind of structure was built originally in around 1500, the problem was that the river was drawing the boundaries between two different states. And in order to solve the water resources management problem, they decided to divide the water that was withdrew from the river to split it 50-50. And therefore they devised this partitore, which means that it's a canal which is cut right in the middle by this divider, in order to split the water into perfectly equal parts. It's still there. It's interesting. Here is another picture of the partitor, of the partitioner. This is from downstream to upstream. The other picture was taken upstream to downstream, and this is the downstream part. You see two different canals. They deliver the same amount of water. These are some canals during the irrigation season, and you see some other structures that allow you to regulate, because these canals for irrigation, they need to be managed. And usually people cannot let the water flow into all of them. They have to make what we call the turnation, which means that when you have to irrigate a large region, you irrigate by sectors. And in order to divert the water from a canal to another, you need these structures. And these were governed manually in the past. Now they are, almost all of them are automatic. Okay, this is a detail of the area where the Parmesan cheese is produced. Let's forget about the details because you are not interested in them. And these are a description of the consortiums for land reclamation. What are their features? I'm skipping the water quality. It's another topical issue, because when you use water for irrigation, water quality is an issue, but I'm skipping it for now. And now let me turn to what was done. First of all, the estimation of the water demands. These pie graphs basically report the results of the estimation of the water demands. What is interesting to see here, and I'm sorry for some words in Italian, what is interesting to note is the totals. So you see that 70% of the water withdrawals are for irrigation. And I mentioned to you that this applies globally. If you want to estimate the water consumption for civil plus industrial use, it's 1/3 of the total. Usually this is a rough estimate, a rule of thumb that applies all over the world. And it applies here. So basically this is the important thing that I wanted to show you. And this is an estimation of the total water demands. In the next graphs, you see an estimation of the demands by source. So basically you see this refers to civil use, and the civil use, water for civil use is got mainly from groundwater. Why is that? Because it's cleaner. If you look at the irrigation, this is industrial, this is irrigation, and for irrigation you see that the largest part of the water is taken from surface water. Why is that? Because it's cheaper. Of course, it's not always available, and when it's not available, they use groundwater. Groundwater, the yellow one. The blue part and the red part are both surface water. This is Po River and this is Apennine rivers. These are details that I wanted to make available to you, but what's interesting is this slide. So basically, what was done here, we identified the domain. And what was the domain? The domain was the area served by the given consortium for land reclamation. So basically, the area where the Parmesan cheese is produced is managed in terms of irrigation by one consortium for land reclamation. And this consortium works over a well-identified administrative area. We took this area as the considered domain. And in particular, in this particular case that I'm showing to you, the domain was the area irrigated by Apennine rivers. Because the area where the Parmesan cheese is cultivated is not irrigated with water from the Po River. It's irrigated with water from the Apennine rivers plus groundwater when the Apennine rivers get dry. So this was the domain identification. For this domain, we performed just we applied the water balance. And keep into account that this equation is in differential form. If you want to make a design over a given period of time, you need to integrate it. Because, of course, you need to integrate to see what happens, because this gives to you only the change in water storage. If you want to understand what happens at a given time, if you want to understand what happens over a long period, which may be the summer period, you need to integrate this equation. And you can, usually, we integrate it numerically by using a fine difference method. So basically, what we wanted to do is to define the terms of the differential equation. Terms, I mean water availability, water demands, and then integrate it. This gives the solution to the problem. Why is that? Because actually, at the beginning of this story, about 10 years ago, we didn't know the water demands and neither the water availability. Meaning that, of course, we listen to farmers who say, I don't have enough water. But if you ask the farmer, how much more water do you need? They didn't have an answer. They can only say that from the beginning of July to the beginning of September, I don't have water. And then I need to pump the water. And if you ask them, how much water do you pump? They couldn't give a reply. They just say, okay, I turn on my pump at 6 o'clock in the afternoon, and then it runs for about 10 hours. But they don't know what is the flow, the nominal flow of the pump. So there was no information at all. And of course, if you don't have any information, you can't design a solution. Because the farmers were asking for a dam. They wanted that a dam was built upstream in the river in order to make a storage during the winter to make sure that irrigation could be granted during the summer. But the problem is that they didn't know what the storage should be of this dam. And also, as an engineer,